A fluid is any substance that flows or conforms to the outline of a container. Both liquids and gases are fluids that follow many of the same rules. However, for all practical purposes, liquids are considered incompressible, while gases are compressible. Much of the science of flight is based on the principles of fluid mechanics. For example, the air that supports an aircraft in flight and the liquid that flows in hydraulic systems both transmit force through fluid mechanics. A solid body submerged in a liquid or a gas weighs less than when weighed in free space. This is because of the upward force, called buoyant force, which any fluid exerts on a body submerged in it. An object will float if this upward force of the fluid is greater than the weight of the object. Objects denser than the fluid, even though they sink readily, appear to lose a part of their weight when submerged. A person can lift a larger weight underwater than they can possibly lift in the air. The overflow can is filled to the spout with water. The heavy metal cube is first weighed in still air and weighs 10 pounds. It is then weighed while completely submerged in the water and it weighs 3 pounds. The difference between the two weights is the buoyant force of the water. As the cube is lowered into the overflow can, the water is caught in the catch bucket. The volume of water which overflows equals the volume of the cube. The volume of irregular-shaped objects can also be measured by using this method. If this experiment is performed carefully, the weight of the water displaced by the metal cube exactly equals the buoyant force of the water, which the scale shows to be 7 pounds. Archimedes performed similar experiments. As a result, he discovered that the buoyant force which a fluid exerts upon a submerged body is equal to the weight of the fluid the body displaces. This statement is referred to as Archimedes' principle. This principle applies to all fluids, gases as well as liquids. Just as water exerts a buoyant force on submerged objects, air exerts a buoyant force on objects submerged in it. The amount of buoyant force available to an object can be calculated by using the formula: if the buoyant force is more than the object weighs, the object will float. If the buoyant force is less than the object weighs, the object will sink. For the object that sinks, its measurable weight will be less by the weight of the displaced fluid. Example: a 10 cubic feet object weighing 700 pounds is placed in pure water. Will the object float? If the object sinks, what is its measurable weight in the submerged condition? If the object floats, how many cubic feet of its volume is below the water line? The object will sink because the buoyant force is less than the object weighs. The difference between the buoyant force and the object's weight will be its measurable weight, or 76 pounds. Two good examples of buoyancy are a helium-filled airship and a seaplane on floats. An airship is able to float in the atmosphere and a seaplane is able to float on water. That means both have more buoyant force than weight. The pressure exerted on the bottom of a container by a liquid is determined by the height of the liquid and not by the shape of the container. 3 different shapes and sizes of containers are full of colored water. Even though they are different shapes and have different volumes of liquid, each one has a height of 231 inches. Each one would exert a pressure on the bottom of 8.34 psi because of this height. The container on the left, with a surface area of 1 square inch, contains a volume of 231 cubic inch. 1 gallon of water weighs 8.34 pounds, which is why the pressure on the bottom is 8.34 psi. Still thinking about, if the pressure was measured halfway down, it would be half of 8.34, or 4.17 psi. In other words, the pressure is adjustable by varying the height of the column. Pressure based on the column height of a fluid is known as static pressure. With liquids, such as gasoline, it is sometimes referred to as a head of pressure. For example, if a carburetor needs to have 2 psi supplied to its inlet, or head of pressure, this could be accomplished by having the fuel tank positioned the appropriate number of inches higher than the carburetor. Pascal's law explains that when pressure is applied to a confined liquid, the liquid exerts an equal pressure at right angles to the container that encloses it. For example, assume a cylinder is filled with a liquid and fitted with a 1 square inch piston. When a force of 1 pound is applied to the piston, the resulting pressure of the confined liquid is 1 pound per square inch everywhere in the container. You can find the amount of force produced by a hydraulic piston by multiplying the area of the piston by the pressure exerted by the fluid. An easy and convenient way to remember the formulas for Pascal's law, and the relationship between the variables, is with the triangle. If the variable we want to solve for is covered up, the position of the remaining two variables shows the proper math relationship. This hydraulic system is a little more complex than the previous one. The input force of 5 pounds is acting on a 0.5 square inch piston, creating a pressure of 10 psi. The input cylinder and piston is connected to a second cylinder, which contains a 5 square inch piston. The pressure of 10 psi created by the input piston pushes on the piston in the second cylinder, creating an output force of 50 pounds. Often, the purpose of a hydraulic system is to generate a large output force, with the input force being much less. The input force is 5 pounds and the output force is 50 pounds, or 10 times greater. The relationship between the output force and the input force is known as mechanical advantage. The mechanical advantage would be 50 divided by 5, or 10. The formulas can be used to calculate mechanical advantages. When gaining mechanical advantage this way, it is important to note that the pistons do not move the same distance. In the previous example, when the small piston moves inward 5 inches, it displaces 2.5 cubic inches of fluid. When this is spread out over the 5 square inches of the larger piston only moves 1/2 inch. The formula illustrates the relationship between the piston area and the distance moved in a simple two-piston hydraulic system. This formula shows that the volume in is equal to the volume out. Part of understanding Pascal's law and hydraulics involves utilizing formulas and recognizing the relationship between the individual variables. Before the numbers are plugged into the formulas, it is often possible to analyze the variables in the system and come to a realization about what is happening. For example, look at the variables and notice that the output piston is 20 times larger than the input piston, 5 square inch compared to 1/4 square inch. That comparison tells us that the output force will be 20 times greater than the input force, and also that the output piston will only move 1/20th as far. Without doing any formula-based calculations, we can conclude that the hydraulic system in question has a mechanical advantage of 20. Thanks for watching.